Continuing our conversation about Newton's laws and forces, I'd like to go over a couple other type of forces that we have not discussed yet, and also I want to do a more involved example that has both an inclined plane and a pulley. So let's actually start with that. So this time we're going to have an inclined plane like this, and let's just say that this angle is, say, 35 degrees. There's going to be an object on this inclined plane, a box. Let's say mass is 5 kilograms. The complication is going to be in this. There is going to be a pulley, and a string connects this first mass, I should have probably actually called it M1, okay, to the second mass M2, and the second mass is 15 kilograms. So the system is released from rest, and just like in the couple of previous problems that we've done, we need to find acceleration of the system and force of tension. Notice how I'm not even going to write acceleration or force of tension as vectors, because just by nature of the problem, we kind of know what the directions are. At least we know for force of tension. So acceleration is actually a little bit ambiguous because we don't quite know what direction the system is going to slide or move. We can make an educated guess. We can say that the system is going to move like that. So this hanging object is going to accelerate downward, and the object on the plane is going to accelerate up the plane. Now again, this is only an educated guess. We're going to basically do this problem in this fashion, making that assumption and following all the signs, minus signs, to be consistent with that assumption. And the way that we're going to know whether this assumption ends up being correct or not is looking at the answers. So if we set up this problem as is and make those calculations based on our assumption of direction of acceleration, and at the end we end up with a minus sign for acceleration or a negative value, then we'll know that we made an incorrect assumption for the direction. Although it's probably going to be fine in this case, because look at how different the masses are, right? That's quite a bit of a difference there. Okay, so first things first, we're going to make a free body diagram, and we're going to do that for each object separately. So here's our M1. By now you should be confident enough in creating free body diagrams that you're able to account for all of these forces acting on the system. Oh, I forgot to tell you that there is also friction, and I need to tell you that mu is 0.3. I guess I don't need all those zeros. Mu is 0.3 there. Okay, so for M1, we got force of gravity. I should call it Fg1. We got normal force, which is obviously perpendicular to the slope. We got force of tension, which is obviously along the rope. And we got force of friction, which is obviously opposite of acceleration. So if you weren't sure on any of those where I said the word obviously, you need to go back and check your understanding of those concepts. We also talked about how in this case it's convenient to define coordinate plane in such a way that the axis, the x-axis, the positive x-axis, is in the direction of acceleration. Y is obviously perpendicular to that. And during the last set of lecture notes, we also learned how to break up this force of gravity into components. So this is going to be Fg1y and Fg1x. So see how I drew this, and then I noticed that my force of normal doesn't agree with the y component of the force of gravity. So I'm going to go back and adjust that a little bit. So you can adjust the scaling of these forces as you go along. You should also remember that now we're dealing with this angle being our angle theta, and that FG1x is now FG1 sine theta, and FG1y is FG1 cosine theta. Remember how sine and cosine switch in this configuration, right? Okay, so let's see. We took care of force of gravity, even took care of its components. We took care of all the contacts, right? We got the plane and the rope, took care of that. We made sure that our coordinate system reflects the geometry of the problem, so that the x-axis in the direction of acceleration. And that's it, right? So this is our complete free body diagram for M1. A free body diagram for M2 should be a little simpler. Okay, so here we have a force of gravity 2, and we have force of tension. Okay, so here acceleration is going to be downward, the way that we decided, the way that we made an assumption. Okay, so the downward force obviously needs to be larger than the upward force. And also remember that force of tension is constant. We're not told otherwise. So we're assuming ideal rope. Okay, so force of tension is constant, so you need to make sure that those two forces of tension have the same magnitude on the two diagrams. And that's it, right? This is a simpler one. We took care of force of gravity, and we took care of the only contact, which is the contact between M2 and the rope. Great. So let's now move on to writing the equations of Newton's laws. Okay, so let's write down Newton's laws. Okay, so here, again, you should be comfortable by doing this by now. For this first object, sum of all forces in the x direction is equal to m1a, and sum of all forces in the y direction is equal to 0. For the second object, we don't have x, so we only need to worry about y, and that's equal to m2a. Okay. So let's see. Back to the first object, let's see how far we can get with this analysis. In the x direction, we have force of tension minus the force of friction minus the x component of the force of gravity. All of that equals m1a. And in the y direction, we have normal force minus the y component of the force of gravity, and that equals to 0. So by now, writing those equations should not be causing you problems. Let's see what else we can do here. So for force of friction, we can substitute mu Fn. That's the x component. And then for the y direction, I can solve for Fn. And instead of just plugging in numbers, let me work this out algebraically, and then let's just keep plugging stuff in as much as we can, as in making algebraic substitutions. So my next step is to write normal force as Fg1 cosine theta, and then I can even take it one step further and write it as m1g cosine theta. Okay, so that's my normal force. I'm gonna substitute this expression into here. And then, of course, I can also substitute the other equation or expression for fg1x. So this is where I am so far. ft minus mu m1g cosine theta minus m1g sine theta equals m1a. So we got our coefficient of friction, we got our masses, we have g obviously, and we have the angle. So basically in this equation we have everything except for force of tension and acceleration. So this is another one of those examples where we're going to end up solving two equations and two unknowns. I'm now going to go to the second object, and this is also something that we already discussed. I want to make a positive direction in the direction of acceleration. So this equation will turn into fg2 minus ft, which is equal to m2a. And I can write m2g for the force of gravity. Once I do that, obviously again we have our masses and our g. So we have the same two unknowns, force of tension and acceleration. So I'm going to use the same approach as I have used in the past and solve for force of tension. Okay. I'm going to do the same thing for this first equation, solve it for force of tension. And because we already said that force of tension is the same throughout the rope, I can set this to expressions equal to each other. Mu m1g cosine theta plus m1g sine theta plus m1a equals m2g minus m2a. Notice that in this case I cannot cancel out the masses because we got a combination of m1 and m2. So I can't simplify it too much. However, I can solve for acceleration. So let me collect all the terms with acceleration on one side. And then I'm going to collect all the terms without acceleration on the other side. And of course, same rule always applies. If you need to make more algebraic steps, please do so, as many as you need. Okay. So I'm going to write the final result here. m2g minus mu m1g cosine theta minus m1g sine theta all over m1 plus m2. Okay, and then I'll substitute all the values in. m2 was 15 kilograms. I need a little bit more room for that. 15 kilograms. Obviously g is 9.8 meters per second squared. Mu was 0.3. m1 was 5 kilograms. G again is 9.8 meters per second squared. Cosine of 35 degrees, I believe. Yep, 35 degrees. Minus, again, 5 kilograms. 9.8 meters per second squared. Sine 35 degrees. And all over the total mass, which was 20 kilograms. Okay. So let's plug everything into the calculator here. And I get acceleration equals 5.94 meters per second squared. Okay. Now remember what we said in the beginning. we're going to make an assumption about direction of acceleration. And if our assumption of direction turns out to be correct, then we should get a positive answer. Obviously, provided we didn't make any silly algebraic or calculational errors. So that's our acceleration. We confirmed by seeing that this is a positive number that our assumption of direction was correct. From there, remember force of tension is the same, so you can pick either one of those expressions for force of tension. I'm going to use the second one because it's obviously easier. So Ft was m2g minus m2a. I can even factor out m2. And then I'm going to plug everything in. And I get force of tension equals 57.9 newtons. Constant magnitude throughout the row. So this was obviously quite a challenging problem. As far as problems with free body diagrams are concerned, I would say that this is kind of as hard as it gets. So everybody should be able to set it up this way and follow this analysis, and then go back and redo it all by yourself just from the statement of the problem. That would be a good practice for any quiz or exam. Okay. Aside from this complicated example, I wanted to go over two more types of forces that we might encounter. One of them is called apparent weight. We'll get to the other one in a few minutes. Okay, apparent weight. And in order to demonstrate what apparent weight is, let's look at an example of a person standing on a scale in an elevator. So here is my elevator, obviously a very schematic representation. There is a scale and a person standing on the scale. So right now this elevator is going to be stationary. I am going to take the mass of the person to be 70 kilograms. That's about an average mass. Okay. And let's see what kinds of scenarios we can imagine. So I'll start with stationary. I am specifically interested in drawing two separate free body diagrams. One for the person and one for the scale. And yes, I said I usually draw the objects as just boxes or dots, whatever. I'm just going to leave it like that. So again, by now you should be well versed in drawing free body diagrams. And for this particular scenario, a free body diagram is not nearly as complicated as the one that we just did. So there is obviously a force of gravity acting on the person. I'm going to call this FGP. And there is a normal force acting on the person, Fn. I'll call this FNP. Right, so that's the support force. So what we need to consider here is where that normal force is coming from. So the person is standing on the scale, not directly on the floor of the elevator. So this normal force is really the force that the scale exerts on the person. Okay, force that the scale exerts on the person. That's it. Nothing else is happening there. Right? So simple free body diagram. For the scale, we have force of gravity acting on the scale. We obviously have the normal force. Normal force on the scale. So this one is provided by the elevator on the scale, or by the floor of the elevator, right? But the other force that we need here is of force of the person on scale. Force of the person on scale. Now remember we talked about action-reaction pairs. So this force here and this force here, those are action-reaction pairs because that's a description of the interaction between the person and the scale. Now, this particular force, the force that the person exerts on the scale, is what we call apparent weight. So the whole purpose of a person getting on the scale is for them to be able to read their weight, right? That's what scales are for. Pretty self-explanatory. So turns out that that number, that value that this person is reading, is a measure of how strongly the person pushes on the scale. Okay, so that kind of makes sense too. But it's also a measure of how the scale pushes on the person, since we got those action-reaction forces going on. Okay, so think about it. Apparent weight is effectively the force that the scale exerts on the person. It's effectively the normal force. Okay, so you'll see why that becomes important in a few minutes. So we're not really interested in the scale itself. Yeah, we drew a free body diagram and we already defined the apparent weight, but that's not essential. Let's just look at what's going on with the person. Everything is stationary. Forces are only in the y direction. That's almost boring right now after all the other problems that we've done. Right? So what we get is FNP minus FGP equals 0. FNP equals FGP. All right. Now remember that FGP is mass of the person times G. I'm going to just assume that G is approximately 10 meters per second squared. Good enough for what we're doing right now. Yeah, if we were doing precise calculations, we probably wouldn't want to do that. And that's fine. So right now we're just kind of estimating things because I want to make a point of discussing apparent weight specifically. Okay? So normal force here ends up being just 700 newtons. Okay, easy enough. So this is what the scale is going to read, right? Remember that the scale effectively is telling us this force, right? So the scale says the person standing on it weighs 700 newtons. You would say mass is 70 kilograms, but you would say the person weighs 700 newtons, as in that's also the force with which the earth is pulling on this person. Cool. So, like, really no surprises here. Let's make this a little bit more complicated. We're going to have our elevator and everything else that's in it. We're going to make accelerate upward. I'm just going to make this acceleration, be 2 meters per second squared upward. Now that's actually a huge amount of acceleration for elevator. If you want to experience that much acceleration, you probably have to go to some kind of a high-rise building, like in Vegas or something. Typically, elevators are not going to have that much acceleration. The fact that it's upward is important though. So I'm sure all of you have ridden in an elevator at some point in your life. So imagine what happens when you walk into the elevator on the bottom floor and you push the top floor button and then the elevator starts moving, starts accelerating. What do you feel? Think about it for a second. So hopefully you remember that feeling. Okay. So let's try to confirm what that feeling actually means. Okay. Now, I'll tell you one more thing before I start writing this down. I'm going to make a claim here that a person can lose weight or gain weight by going into an accelerated elevator. And you can laugh at my claim, or we can keep going through this problem and see if my claim is correct. I'm only going to consider for a free body diagram of the person. The scale is not important. The only reason I drew that free body diagram of the scale before is because I wanted to address that action-reaction pair. But now it's all about the person. So, remember, there is force of gravity acting on the person. I'm going to be very careful and draw it exactly the same length as I had before. So nothing has changed. The elevator is still near the surface of the earth. The person's mass did not change. So the gravitational attraction to earth is exactly the same as it used to be. What changes is the upward force, right? Because now we have this upward acceleration. That means that the upward force has to be enough to overcome the downward force and to provide the upward acceleration for the person. So this time, when I write sum of all forces, it's not going to be 0. It's going to be mass of the person times acceleration. And then I'm going to write FNP minus FGP equals MP times A. And again, I'm going to solve for FNP. Okay, we already know what FGP is, right? So that we calculated in this previous part. FGP was 700 newtons. 700 newtons. Mass of the person is still 70 kilograms. Acceleration is 2 meters per second squared. So if I do this calculation, I have 840 newtons. Oh, that's interesting. So the person is standing on the scale, and the scale now shows 840 newtons. In comparison to the previous measurement, the previous reading of 700 newtons. Huh. Now remember that FNP is our apparent weight effectively. So when this person stands on the scale and looks on the scale says 840 newtons, the person goes, oh, I gained weight. Alright, so that part of the claim is okay so far, working out. You should recognize the feeling. When you go into an elevator that accelerates upward like that, you feel quote-unquote heavier. So what you're feeling is that increase in the normal force. The floor of the elevator pushes you up because it needs to overcome your force of gravity and to create that extra upward acceleration. So now do you think the other half of my claim is going to be correct? Where a person can also lose weight in an accelerated elevator? I hope you said yes to that. So same exact situation. Person standing on the scale. The elevator is now accelerating downward. I'm gonna keep it at 2 meters per second squared. Just easy numbers, right? We'll draw our free body diagram on the person. Same FGP. But now you should be able to conclude this. FNP is not enough to overcome force of gravity. Right? So it's a downward acceleration. That means that downward force is larger than the upward force. Except it's not because of increased force of gravity. The earth pull on the person did not change. Everything's the same. So the only thing that's going on here is that feeling of the floor falling away from underneath you. So that's because the floor of the elevator, well, in this case, the scale, is not pushing as hard on you. It's not enough to overcome that force of gravity provided by the Earth. So just as before, I'll make that a positive direction, aligned with acceleration. And I'm going to go through all of this setup and all of these calculations again. So be careful with minus signs. Okay, so I'm going to solve for F and P. This is going to be FGP minus MPa. So 700 newtons minus 70 kilograms times 2 meters per second squared. This gives us 560 newtons. Ooh, okay. So the person did lose weight by going in an accelerated elevator. So it's totally possible to gain weight or lose weight in an accelerated elevator. The problem, of course, is that in physics, losing weight or gaining weight does not mean exactly the same thing as it does in English or other spoken language. Usually when we say, I want to lose weight or I gain weight, we don't mean that, right? We mean, I want to gain mass or I want to lose mass. I want to change the composition of my body or the number of particles that my body is made of, right? So this apparent weight loss or weight gain is not lasting. It's only happening while the elevator is accelerating. So as soon as the elevator stops accelerating, we're going right back to that first scenario. Yeah, I wrote stationary here, but I really should have said equilibrium, right? I really should have said acceleration is equal to 0. Because it really doesn't matter if velocity is 0 or if it's just constant. What mattered in that the first part, is that the forces were balanced, right? So if an elevator is moving at constant speed, that's still going to be exactly that. So this weight loss or weight gain is really short-lived. It's not even while the elevator is moving. It's only while the elevator is accelerating. Okay, so then let's think about a kind of a worst case scenario in a sense. So this elevator is accelerating downward, right? And then all of a sudden the cord breaks. Now in real life you don't have to worry about something like that because there is all kinds of safety cables. It's not as simple as just one cord. There is all kinds of brakes and other safety devices attached to the elevator. So this would never happen in real life. But again, I'm only doing this to simplify math and to make a point. Okay? So let's assume that the cable breaks. So now, what's this acceleration here? It's not just any random acceleration, right? It's free fall. So there is no support for anything anymore. No tension, no normal force, nothing like that. So everything is accelerating downward at the same rate. So if there was some kind of a camera on the interior of the elevator, the camera would see a situation that would appear to us as what we call in everyday English as weightlessness. And the reason for that is because everything that's inside of that elevator is accelerating downward at the same rate. So the person, the scale, and the elevator floor, they're like all trying to catch up to each other, and they can't because they're all accelerating downward at the same rate. So you kind of see this floating in the air kind of deal. If you've ever watched like NASA TV or anything else where they're showing space station, how the astronauts are kind of floating in space, that's what that is. So it's not really weightlessness. It's what I'm calling in quotation marks, weightlessness. Okay? So because there is no contact anymore, the normal force is equal to 0. Now, if I wanted to draw a free body diagram here for the person, guess what? there is only force of gravity acting on that person. So weightlessness is not really the absence of weight, because Earth is still pulling on that person. Weightlessness is kind of a misnomer. It's the idea that there is no apparent weight. There is no support. There is no contact between the person and the scale. So it looks like the person is floating, but really that person is just accelerating at the same rate as everything else. It's actually very similar to a spaceship. This is not a circle. A spaceship that's orbiting Earth. This is like way not to scale, but it doesn't matter. So we'll talk more about circular motion and all of that. But I just want to throw this picture out there so you can start thinking about it. So when it comes to a spaceship or a space station that's orbiting around the Earth, all those astronauts are quote-unquote weightless because there is still the same acceleration for everybody. And that acceleration, you should be able to figure that one out, that's the centripetal acceleration there. So it's no longer gravitational acceleration, or it's no longer equal to 9.8 meters per second squared, but it is a constant acceleration for all the objects on that spaceship. We'll talk more about that in the next chapter. But that's really kind of it, right? So again, one of those things where English and physics don't necessarily have the same meaning. So quote-unquote weightlessness is essentially free fall. There is only force of gravity acting on the person that's quote-unquote weightless, which is like totally against common sense, right? But that's how physics works out in this case. Okay, so the last piece of information, the last type of forces that I would like to discuss here is a force of drag. So we obviously talked about friction before, and the difference here is that in physics, typically when we say force of friction, we're referring to friction between two solid surfaces. And when we say drag, this is like friction or resistance between a solid surface and fluid. So fluid is defined as something that can flow, so liquid or gas. Don't concentrate on that right now. We're going to do a whole chapter on fluids, but not yet. Okay, so basically this is a solid object moving through fluid. It could be something like a person walking through air. You know, when we walk on the surface of the Earth, we're surrounded by air. It could be something like a parachute, or a person jumping with a parachute. It could be something like swimming through water, and so on and so forth. So a solid object moving through a fluid. Turns out that there is actually two situations for force of drag. One situation is where a force of drag is proportional to speed, and the other one is where a force of drag is proportional to speed squared. Now, your textbook goes a little bit more into difference between those two. I'm going to just tell you that that first case scenario, where a force of drag is proportional to speed, this happens at low speed. And the situation where a force of drag is proportional to speed squared, this happens at high speed. Your textbook also goes a little bit more into how to define low speed and high speed. I'm not going to get into that. So there is no like actual cutoff for where the speed switches from low to high. No cutoff, it really depends on the situation. You know, what could be considered high speed for a snail is not high speed for a car, right? So it really depends. So in the problem, I would tell you, utilize low speed equation or utilize high speed equation. In fact, I'm not even going to give you the low speed equation. So we're basically just going to stick to this scenario when it comes to problem solving. Okay, so why is there this discrepancy? Well, let me just show you this. I'm not even going to do any kind of calculations here, but let me just show you an example. So let's say a person jumps out of an airplane. A person has a parachute on, but the parachute is not open yet. So at this point, this person experiences force of gravity acting on him or her. When, actually, let me write this too. At this point in time, the person just jumped off the airplane, so speed is 0. There is no other forces acting on the person besides force of gravity. As the person falls, still parachute is not open, but now the speed is no longer 0, right? So now, aside from force of gravity, there is also a little tiny force of drag acting on the person. Tiny because the speed isn't high enough. The more the person falls, the higher his or her speed, so the more force of drag is. Right? So higher speed. And then, of course, somewhere down here, this person is going to finally open the parachute. Something like that. So now there is going to be a higher force of drag. It's actually not just because of speed, but also because of a really high surface area of the parachute. I'll talk about that in just a second. Right? And then the person is still moving, but eventually these two forces are going to be equal to each other. Not right away, but eventually. Okay, so going back to those two statements about force of drag, in the beginning, if you needed to calculate that force of drag, you would use the low speed equation. As the speed increases, eventually you would switch over to the high speed equation, but the speed is still increasing, right? There is still acceleration going on. And so eventually, force of drag is going to increase because, well, speed still increases until that last case scenario happens. And if Fd is equal to Fg, acceleration is equal to 0. So that speed at which that happens, we call that, I'll call this Vt. This is called terminal speed or terminal velocity. So that's the highest velocity that an object can accomplish, and that only happens when force of drag is equal to force of gravity. So let me give you an actual equation that allows us to calculate force of drag. The one that we're going to use, there are a couple different ways of writing it, but this is how I'm going to write it. 1/2 capital C rho A V squared. So this I'm going to box. V, that's kind of self-explanatory, that's speed. This letter here, this is a Greek letter rho, don't call it P. This is density. So we have not talked about density yet, but you probably know this from previous science course or maybe even from like middle school. This is mass over volume. I'm not going to concentrate on that right now, but this is density of fluid. So in the case of the person jumping with a parachute, it would be density of air. Density in this case is measured in kilograms per cubic meter, right? Because it's mass over volume. Okay. And it's something that you can either find that value in a table or something that I would have to give you. This A here is called cross-sectional area. And that has to do with like area, quote unquote, into the wind. And by the way, that capital C, which is called the drag coefficient, that also depends on what faces the wind. Okay, so a couple of examples of that. Talking about the person in the parachute, jumping with a parachute, we can model a person kind of like as a cylinder. And here it's this area, the bottom of the cylinder, that faces the air, right? So force of drag would be like this. So that bottom area, the circular area, is what faces the wind, or what faces the drag. Okay, so obviously you know how to calculate area of a circle, but for something like this, C, that's a unitless constant. This is 0.8. You do not have to memorize these. I will tell you what C is for different shapes. If a person was kind of falling flat on their back, like this, the area that would be facing into the wind would be this rectangle. So imagine taking a cylinder and slicing it horizontally in half. So this would be A, and in this case, C would be 1.1. If we have a sphere, which is kind of hard to draw because it's supposed to be three-dimensional, the area is, again, this circle, right? So imagine taking a sphere and slicing it in half. Okay, and in this case, C is 0.5. So you get the idea. So the actual area depends on which way the object is facing, towards the wind or towards the airflow, and C depends on the shape of that area. Not on the number, but on the shape. So then you take all of these values, plug that in, and you have force of drag at quote-unquote high speed. So if I ever ask you to calculate anything else of the sort, I will give you C and rho. Area, well, you might have to calculate it, so it's going to be either a circle or a rectangle, so that's easy to calculate. And then obviously speed, you'll know, or maybe you'll have to calculate that. And then that's how we're going to define drag force. And then of course, just like any other force, the drag force is measured in newtons. So this is kind of it for forces, although we're still going to be talking about some other types of forces in the next chapter. And then we're going to also keep utilizing forces pretty much for almost the rest of the semester. But these are all the kind of important ways of addressing forces. We've obviously discussed how to apply Newton's laws, right? You need to be able to state Newton's laws, draw free body diagrams, and so on.